Hello, in this video I'm going to take a first look at the ideal gas laws, and it's a first look because I'm going to be approaching from the classical thermodynamics macroscopic perspective on this. Now later on we'll start looking at the microscopic underpinning for these gas laws, but at the moment we're going to be looking macroscopically. So we're going to take our three main macroscopic properties of gas. So that is pressure, volume, and temperature. And we're going to see how these things are related to each other. You know, how does one thing change if we change the other one? Now, there are theoretical underpinnings to this that we can unpick mathematically at the microscopic level. But when we're at the macroscopic level, as they were in the early days of classical thermodynamics, we're looking here at empirical results. These are the findings of experiments and observations. So yeah, let's approach it from that end. And that brings us into the first one of three relationships here that we've got between these macroscopic properties. And that is Boyle's law, which gives a relationship between pressure and volume. So this is named after Robert Boyle, who was doing his experiments in the 17th century. And he found that under certain conditions, and I'll get onto those conditions in a moment, the pressure of a gas is inversely proportional to its volume. But this is only applicable for constant temperature and a fixed mass of gas. And this is really important, these conditions here. If you don't have this constant temperature and fixed mass, then Boyle's law does not hold. So really, really important. Now, I'll come back to that in a moment with why these things are so important. But first, I'm going to make note of the other two laws that we've got here. So we've got Charles's law, and I've done a separate video on Charles, the French, I think it was Jacques Charles, who was the French scientist who had this law named after him, and he was looking at temperature versus volume, found that the temperature is proportional to volume for a gas. But here we go again for constant pressure and fixed mass of gas. And then we've got the Gay-Lussac's law. Again, I've done a separate video on him. And this is then giving a relationship between pressure and temperature, saying that pressure is proportional to temperature for a gas, and you've guessed it, for constant volume and fixed mass. Now, the importance of these conditions here is quite easy to see, actually, when you start digging around. Let's start digging around in Charles's law. And you think, well, okay, we start with, say we've got some volume of gas, and we know we're dealing something here to do with temperature. We know what volume means. We know that temperature is a measure of the average kinetic energy of the particles in the gas. So we've got all of these particles inside this box. They're all moving around with a certain average kinetic energy. We then increase the volume, and we've got all these particles still flying around. We've got the same number of particles, so we've got a fixed mass. That's all great. But the thing is, you see, I mean, that isn't immediately going to bring us to Charles's law. We can't just say, oh, yeah, great. Now, what does that tell us about the temperature? Because, well, everything here has still got the same average kinetic energy. You know, nothing's changed. These particles, in terms of the energy that these particles have got, they're still moving around with the same average speed all the way around here. The kinetic energy hasn't changed. We haven't put any energy into the system. Nothing's made any difference. So what we've actually got there is Boyle's law, that we've got a constant temperature because the average kinetic energy hasn't changed, and we've increased the volume, which means the pressure would have decreased because pressure is inversely proportional to volume. So that's all great. You know, we can now see, yeah, that makes sense with Boyle's law. You know, we've got fewer collisions going on, and this is what we're going to be looking at when we get to the microscopic underpinnings of these ideal gas laws. We've got fewer collisions between the gas particles and the walls of the container. So the pressure would have gone down because you've got less force being exerted on the outside of the container. So that is a demonstration of Boyle's law. Now let's go back and think, well, actually, we wanted something to do with Charles's law. We want to increase the volume and see what happens with the temperature. Well, yeah, well, if we increase the volume at constant pressure, well, that makes the whole world a difference, because now we're at this larger volume, but we still need to be having the same pressure exerted on the outside walls, which means we're going to need the particles inside the gas to be traveling more quickly so they can exert more force per impact and have a larger number of impacts than they would do if we hadn't have put any more energy into the system. So in order to maintain the pressure as we go from small volume to large volume, the temperature has to increase. It's the only way we can actually do it. So in the same way as if we'd had it the other way round, that we had started off with this small volume, we'd pumped a whole load of energy in. Well, in order to keep the pressure constant, well, we have to increase the volume. So we can think about these relationships, how it's all underpinned by looking at each one in turn, and why these fixed, having a constant temperature or a constant pressure, excuse me, is so important in maintaining these three gas laws. So that's why that's crucial. Right, you can combine these gas laws into a fourth gas law, these are three gas laws, fourth gas law, which is particularly important. So let's say then we've got some set up initially where we've got some pressure P1, some volume V1, some temperature T1. And we want to get from that setup to some other combination. We want to do something to this gas in this initial state to get to a P2, a V2, and a T2. So we changed everything. We've got an initial set of pressure, volume, temperature. We want to get to some other set of a different pressure, a different volume, and a different temperature. Right, so how are we going to go about doing that? Well, we can't just change everything all at once and get it to obey these laws in between. We can't combine all three of these laws here, Boyle's law, Charles' law, Gay-Lussac's law, because two things can vary and the third thing has to be fixed. We've got a constant temperature, a constant pressure, and a constant volume. I mean, you can have a whole load of stuff changing, but it's then not giving you the relationship between the quantities as they're changing. It's kind of just like a free-for-all where we're losing control over how these things are related. We can't take a path, a mathematical path, from one set of macroscopic properties to the other. It's just a case of, oh, well, we started here, we end up there, but we've got no idea how we've got from one thing to another, and we don't know how these two sets of things are related to each other. We want to find a path that we can use these three laws and say, aha, right, well, because we followed these laws, we can say how P2, V2, and T2 are related to P1, V1, and T1. And we can't do that unless we follow these three rules. So in order to follow these three rules, we need to go through some intermediate set of states. So let's say, rather than just going straight from set 1 to set 2, we're going to start off by, let's say we're going to use Boyle's law. So we're going to fix the temperature. So we're going to go to some state T1. We're going to change the pressure to what we want the end pressure to be, so P2. And we're going to change the volume to some whatever volume it would be in order to get the pressure that we want. So you can see how this is following Boyle's law. We've said, right, all we care about at the moment is changing our P1 to P2. Keep temperature fixed. The volume, yeah, well, something's going to happen with the volume. We don't really know what. Now, with Boyle's law, another way of writing Boyle's law, if you think of this proportionality that we've got here, is, so we could say, well, let's turn that into an equation. So pressure is equal to some constant. Actually, I won't use K because that looks too much like the Boltzmann constant. So some constant C divided by V. So we can say from Boyle's law, another way of writing it is pressure times volume is a constant, providing we stay at a constant temperature. So we can say off of this that P1 times V1 is going to be equal to P2 times this V star, whatever it may be. So we now know that V star is going to be equal to P1 V1 over P2. So great. Right, so now let's go. We've gone down to this state. Now let's get another one of our properties in place. So, well, in fact, we could use Charles's law and we can say, right, well, let's just go straight to the end result because Charles's law is the one where we're not changing P. Let's keep P fixed at P2 and let's head straight over then to P2 V2 T2 because we must be able to get to P2 V2 T2 because we're already at P. There must be something we can do according to Charles's law in order to get the V and T where we want them to be. So wonderful. Now we can do the same thing with Charles's law as we did with Boyle's law. And we can say, okay, then, well, V divided by T is equal to a constant. So we can do the same thing again. We can say that V star divided by T1, as in what we've got from Charles's law in our intermediate state here, is going to be equal to V2 divided by T2. So now again, we can say what V star is. So we can say that V star is equal to T1 V2 over T2. Now we've got two equations related to V star. So let's just equate these two things together and get all of the ones on one side and all of the twos on the other. So as in we can multiply this one by the P2 there, and we can divide this one by the T1 there, set them equal to each other. And then we've got P1 V1 over T1 is equal to P2 V2 over T2. So we've got a new relationship between pressure, volume, and temperature, which is great because now we've got something we can say is always a constant. Yeah, this finding here of our PV over T, this is going to be equal to a constant. Okay, I can't write the word constant in there because I've run out of space on the screen. But that is equal to a constant for a fixed mass of gas, however we're changing the pressure, the volume, and the temperature around. So we're no longer then bound by all of these constraints here and just changing two things at a time while keeping the other one fixed. Because now we've shown by combining all three of these laws together that actually pressure times volume divided by temperature is always a constant for a fixed mass of ideal gas. So that is a very, very powerful law that we've got there. So the last thing that I want to say on this before we then make the transition into looking at the microscopic underpinnings on all of this, and this is just going to start touching into it. I'm going to change colour because I'm running out of space. Is now we've got this PV over T as a constant. So say we were going to turn that into an equation. So we've got PV is going to be equal to some constant multiplied by the temperature. That's what we're saying off of this equation down here. So what is this constant? We have got two ways of filling in that constant. We've got the macroscopic way of looking at it, where we can say, okay, at a macroscopic level, we're thinking about, sort of how much substance have we got? We're looking at a molar level. So we want to say something about the number of moles of the substance that we've got, because when we're looking macroscopically, we're talking about moles of substance. So we can denote the number of moles with a lowercase n. And then we've got a constant of proportionality in order to fit all of this together, which is R, which is the molar gas constant, and R is equal to 8.31 joules per mole per Kelvin. So we've got a molar gas constant there. So we've got one version of this equation then, which is PV equals nRT, and that's a lowercase n. So the pressure times the volume is equal to the number of moles multiplied by the molar gas constant multiplied by the temperature. Now, where this is now going to take a little toe into looking at a microscopic level is, well, what if we weren't looking in terms of moles then? What if we were looking in terms of the number of particles that are actually in the gas? So now we want a different constant that's in this. We've still got PV and we've still got T, but now we've got a different constant. We've got N, a capital N, because we're now looking at the number of particles rather than the number of moles. And then we've got a new constant of proportionality, which is the Boltzmann constant. And I've really done that. I'm going to drop down the bottom left here to write out the Boltzmann constant. So our Boltzmann constant is 1.38 times 10 to the minus 23. So you can see how we're really dropping down serious numbers of orders of magnitude here. Because, of course, we would be, because we've switched from moles to individual particles, which I'll come back to in a second because I want to put the units on here. Joules per Kelvin. So no longer joules per mole per Kelvin because we're working with individual particles rather than moles. So this then, the Boltzmann constant, all we're really doing is saying, well, we started off with number of moles times the molar gas constant. We've ended up with number of particles times the Boltzmann constant. And that's because the Boltzmann constant is equal to the molar gas constant divided by Avogadro's number. That's what we're doing there, because that's the relationship between the number of moles and the number of particles. If we divide one by the other, we've got our Avogadro's constant. Avogadro's constant is the number of particles in a mole. And we've got the same relationship here between the molar gas constant and the Boltzmann constant, that they're related by Avogadro's number. So this then is giving us a switch here between the macroscopic, where we're doing calculations using number of moles and the molar gas constant, and the microscopic, where we're doing calculations with number of particles and the Boltzmann constant. So that's what I want to push on to in the next video, by looking at these microscopic underpinnings of these relationships, these three macroscopic laws, and then what more that can tell us about the kinetic energy of individual particles inside the gas. So yeah, there's an enormous amount kicking around in here, and you can see why they simplify it a bit when you deal with these ideal gas laws at A level. They don't usually derive this law here. It's just adding in a bit more complexity than a lot of people would like. So it is pushing on to sort of first year undergrad type level physics here, but it's not that hard to get your head around, really, I don't think. So, and I think that that distinction between the macroscopic and the microscopic is so important when you're dealing with, well, thermodynamics, but physics in general.